So imagine we have a planet, and that planet is spinning through space. Well, the temperature of that planet is going to be controlled by how much energy is coming in and how much energy is leaving. Okay? So if there is more energy coming in than there is leaving, that energy will get stored as heat. So that the planet will warm up if there's more energy coming in, and it will warm up to the point where the thermal emissions match the incoming radiation. Now, if the converse is true, if there's less energy coming in than there is leaving, the planet will cool down. That's just how it works. You can do this with any object. It doesn't have to be a planet. So the planet's always trying to achieve thermodynamic equilibrium, but you can remove the word thermodynamic and just think of it as equilibrium. It doesn't have to be that complicated. So if this planet is cruising through space and it's not getting any sunlight, it doesn't have any internal source of heat, this planet's going to be at absolute temperature, or absolute zero, so minus 455 degrees Fahrenheit, maybe just slightly above. But planet Earth has some internal heat that's coming from its formation many billions of years ago. And the temperature that that planet would have if it had the same thermal structure as Earth would be minus 400 degrees Fahrenheit. So still, there'll be no liquid water. Everything will be frozen. A much colder planet. But luckily, our planet is very close to the sun. So that gives us a lot of energy coming in from the sun. We have this internal heating from within the Earth. But the temperature, because of all of those inputs, still only equals 0 degrees Fahrenheit. So life as we know it right now would not exist if we just had the sun and we had the internal source of heat. So what we require for liquid water on our planet is an atmosphere. Now that atmosphere has CO2 and other greenhouse gases. And what that helps do is it reduces the efficiency with which the Earth can get rid of its heat. So that it can be at a warmer temperature and lose less heat. So it's just a blanket. You're in bed, you put a blanket on, it warms you up. It operates very much the same way. And as we move into the future, next 100 years, next 200 years, we'll have continued decrease in temperatures, and that's simply because we're thickening the atmosphere. We're adding more CO2 that makes it less efficient for the Earth to get rid of its thermal energy, and that will lead to warming over the next few years. Now that's just kind of from basic thermodynamic principles. You don't have to go back to physics to understand this, but we also have empirical evidence of how this system works. And that comes from ice cores. So ice does all sorts of different things in our climate, but one amazing thing it does is it preserves a very detailed record of the climate history, because the snow falls on the ice, that snow compresses, and then it traps air in little tiny bubbles. Then we can go down to the ice sheets. We can find a place where it's flowing very slowly and where we expect the oldest ice to be. We can set up these massive drill rigs, and we can drill cores down all the way to the bottom of the ice sheets on the order of 3 kilometers thick. And then we can take that ice out and we can extract the bubbles from within that ice, and we can measure how much CO2 is in those bubbles relative to the other components of the atmosphere. So we know exactly how much CO2 was in the atmosphere over a record of almost 1 million years, 800,000 years. And then we have all this other detailed information in there as well. We can actually determine what the temperature was at that time, and it has to do with a complicated relationship between the weight of the oxygen isotopes and the distance it travels and the temperature of the atmosphere. But all that matters is you find a very robust link between temperature and CO2. So on this graph, in blue, you have your CO2 record for 800,000 years that has been extracted from this core. And that's actual measurements of CO2 from the bubbles of the air. And in the red curve, we have the proxy for temperature. And you can see that the two follow each other incredibly well. And that's because the two are driving and reinforcing each other. And to put this in perspective, this time scale, so one of the problems with trying to grasp the direction that we're heading is we have, as people on Earth with finite lifetimes and finite geographical coverage, we have issues with scales, and so we're not able to perceive what will happen out 200 years. We're also not able to perceive what the whole Earth will do. But on here for scale, at 200,000 years ago, I marked the place where modern man first appeared, right? So modern man grew up in a climate where CO2 and temperatures varied by this much. And then also for the 600,000 years before that, the climate has been fairly stable. And Richard Alley says it best, is it's nothing more difficult than when CO2 goes up, temperature goes up. Okay, so you can think of this graph here as natural variability within the realm of what humans have experienced since appearing. Okay. So in 1940, concentrations in the atmosphere were about 280 parts per million. NASA has instruments up right now that can measure the concentrations of CO2 combined with records on the ground. And we now know that in 2017, we've broken 400 parts per million. We're now at 405, I think, parts per million in the atmosphere. So we're well outside of the range of what's been experienced over the last 800,000 years, which is quite stark. And if the relationship to temperature holds, which it does, we can expect that there'll be changes in the climate. Now, the purpose of us at JPL is try and figure out what those changes are going to be. Now, that's where we are now in 2017. Now, the question is where are we going to be in 100 years? Unfortunately, CO2 is a very slow process. It can take thousands of years to get it out of the atmosphere. So once it's up in the atmosphere, you're fully committed for a very long time. And the other thing is it doesn't matter how much you emit in a given day. All that matters is how much you emit over the whole lifetime of emissions. So it's a cumulative process. So let's see what the concentrations might be in 2010. So if we get really aggressive with climate policy, we start having some broad agreement between the major nations and get the developing nations on board, and we have peak emissions by 2040, we would have about a 3-degree Fahrenheit warming. Now, if we're a little bit slower but still ambitious, and we have peak emissions of greenhouse gases in 2060, we'll have a plus 4 degrees Fahrenheit warming by 2100. And if we simply just operate as normal, we account that technology will provide some efficiencies in emissions. We assume that population growth will start to slow a little bit. We assume that there'll be an equal distribution of wealth, so the poor nations will start to equalize with the fully developed nations. This is where we'll end up. Right? So we're looking at just under 1,000 parts per million in 2100. Now, this is to scale. This is to scale, and at the bottom of that scale is the last million-year record of CO2 and temperature. So there is no question that we are going to see fundamental changes in the climate that we have not witnessed before. And because of that, we're trying to determine what exactly those changes will be. There's some that we know for certain. There's others that we're not so certain about. Okay, one thing we're certain about is that the warming starts slowly. So I have 3 different emission scenarios here, from the very top to the bottom, so low scenario to high scenario. And you'll notice out in 2020 that the difference between the worst case and the best case all look exactly the same. But by the time you go out to 2100, they start to look radically different. So this tells us that if you're waiting to feel it, it's already too late because you've already cooked in a temperature into the future that will be much more severe than it appears today. And the other thing you'll notice is that the heating is not evenly distributed. There's quite a bit more warming at the Arctic, which has to do with how the snow responds. So as the snow melts, you reduce how bright it is. That absorbs more energy. So there's these feedbacks that operate in the Arctic that don't operate in other places of the world. And this causes a much warmer Arctic in the future. And there's a lot of ice in the Arctic, and so that starts to matter. Okay, so where does all the energy go? Well, almost all the energy, over 90% of the energy, goes into the oceans. So the oceans are a giant uptake of the additional energy. Also goes into warming the atmosphere, not as much energy. And then some of that energy goes into melting ice. So in this bottom graph, you'll see all the yellow places. That's everywhere where there's ice that's on land, right? So I'm ignoring the sea ice, which is already floating, and because it's already floating, it won't contribute to changes in sea level into the future. So this is where we are. Unfortunately, we're already in the part where we're starting to feel it. 2014, 15, and 16, warmest years on record, so 3 consecutive years in a row. 16 is really pushing the upper limits there. The figure that I'm showing on the left is what the spatial pattern of the 2016 warming looks like. And lo and behold, we have a much warmer Arctic than other places. So it's a pattern that's not too unfamiliar to the climate models that are trying to simulate what happens in the future. And I just want to make a quick note here is that these lines are bouncing around. There's all sorts of different complicated things that go on in the system. But if you look long enough, it just turns into noise. And so one of the discussions going on specifically, I think this started yesterday, was talking about a hiatus. And the hiatus is just because we have this internal variability within the system. And so that's really just focusing right on that red line that I've drawn on the screen there. And you can see that discussion is it's purely irrelevant once you put it in context of a much longer record of temperature. So don't get distracted by the wiggles. Just look at the trends. So a few degrees matter, and that's kind of the other part that's really difficult for us to perceive, because we go through the seasonal cycles, right? I mean, I'm from northern Canada, and we can go from plus 40 Celsius to minus 40 Celsius in a given year. And so when somebody tells you it's going to warm by 2 degrees, it's very hard to envision how that could have any impact on your life. And so this is one of the slides I like to show to illustrate. This is 4 degrees C, so about 9 degrees Fahrenheit, difference in temperature. And this is how different the planet looks. Okay, so 12,000 years ago when we had the Laurentide ice sheet covering all the way, pushing down into Boston, it was creating Cape Cod. There was probably about a mile of ice right over top of Boston. The climate was only 9 degrees Fahrenheit cooler. Present day, we warm the atmosphere by a little bit, and you can see how sensitive the ice is, right? It's all retreated. There's been about 100 meters change in sea level since that time because all of that ice that was on land has now gone back into the ocean. And as temperatures warm, sea levels rise. Sea levels are rising because of 2 things. Warmer water is actually just a little bit less dense, so it expands just a little bit when it heats. And then also you have all of the water leaving the ice that's on the land going into the ocean. That causes the oceans to rise. And you'll notice the units. The units are 3.4 millimeters per year, right? Millimeters. So my first big paper that I published, they ran an article in the local paper where I had grown up. And I was very proud of it. And then the following weekend, there was an op-ed by a geology professor saying that a millimeter is the thickness of a pencil, and that can't matter. So he's provided me the motivation to explain why the millimeters matter. If sea level rose by a millimeter, we really wouldn't care. The problem is it's millimeters per year. And when you add things over time, they start to get to be bigger numbers. So you do that, 100 millimeters or 1,000 millimeters is a meter, right? And that's kind of on the range that we're expecting out by 2100. And if you go to Miami Beach and you tell somebody that sea level at that rate doesn't matter, they'll probably beg to differ. Now when you move that sea level rise to 2 meters, you've lost a lot of real estate there. And it doesn't flood overnight. What happens is you raise it by a meter, and then the next time that storm comes, that would have otherwise just kind of gone up against the water break, now it goes over the water break. And at some point that starts to cost a lot of money. So people in Florida are very interested in what we're doing. They're interested in 2 ways. One, they want to know how to mitigate. And second, they want to know where to retreat. So unfortunately, Florida is mostly limestone, right? Karst landscape. So it's Swiss cheese underneath Florida. So you can build a wall to keep the water out, but it will just go under in a lot of places. So you have to decide what you want to do. Okay, so what does this CO2 future hold for us? Well, I said there's a lot of things that we don't know, but there are some things that we know for certain. We know that the Arctic will green, and it already is greening. So probably agricultural productivity in Canada will go up in the future because now they'll have more land that they can farm. We expect increased frequency of floods and droughts. This is the wet gets wetter and the dry gets drier. Ocean acidification, this is going to have large financial consequences and biological consequences. So This is the stories that you hear about the coral reef bleaching that has to do with the acidity of the water. You'll have loss of sea ice and polar habitat. So there are some creatures that have to have sea ice to live. If there's no sea ice, they don't live. That's just the way it is. I don't think they can move anywhere else. And then there'll be mass migration and adaptation by animals, by different species. But I think probably most significantly to us, it will be the people that will have to move around. So places that are under environmental stress now may become under more environmental stress in the future. And so simply closing a border might not work. And then lastly, it is with almost certainty that sea level will rise in the future as glaciers melt and the oceans warm. And that's the focus of this talk today. So it's just one little small component. But this whole set of slides was simply motivated by my surgeon looking over my head as I'm about to go under. And I thought maybe I should review that one more time. Okay, so there's the review. Now we're going to talk about the sea level rise. Okay, so how will glaciers respond? Well, the most obvious one is that they will increase melting from the atmosphere. So that's probably what everyone envisions. You have a glacier, you warm up the temperature, and it starts melting from the top. And then there's all sorts of really interesting things that happen because as soon as you start to melt it, it gets darker. If it gets darker, it gets more energy. If it gets more energy, it melts more. And so there's kind of these feedbacks that happen. The other one that you might not think about as much, and that's actually more important, is melting by the ocean. So all of the major ice on Earth pours down off the continents and then flows out into the ocean. And so the rate at which the ice enters the ocean is being controlled by how fast that ice is being melted at the ocean interface. And then this has to do with changes in the calving rate. So that is, remember, there's solid ice that's flowing down into the ocean, and then solid pieces of ice are actually breaking off, floating, and then sinking the Titanic, right? So we know that solid ice floats into the ocean. So this is some beautiful drone footage from the Greenland ice sheet. I'm not sure what year this was. This is just one of the melt channels. And there's all sorts of really interesting things that go on that we try and understand. So one is just how is the ice melting? How does it become darker so that we can estimate how much it will melt into the future? But then all of this water will flow down this stream, and eventually it's going to find a crack in the ice. And that crack in the ice, it's going to go all the way down to the bottom. It can go down 1.5 kilometers all the way to the very base of the glacier. Now you have all of this water flowing underneath the ice, and in some cases, it can cause it to speed up. And so those are the types of processes that we're interested in understanding, because if in a warmer world we have more water, we're interested to find out whether that will also affect how the glaciers flow. Now, probably more impressive is calving. And now, what you're going to see here, I should get the pointer here, is this face here is 1 kilometer wide. It's probably, you're only seeing the top, right? So it's a floating ice. It's about 0.5 kilometer high, and then it's going to calve back about 0.5 kilometer. And you see the noise has woken this person up at 5 in the morning, and they're starting to get really curious about what's going on, but it's too cold, so they go back in the tent. But then they hear a big bang, and they come out again, and all of a sudden, that's 0.5 cubic kilometer of ice that just calves off into the ocean. So that is about just under 1% of all of the ice in New Zealand that just broke off in one go there. I'm going to let it loop through because it's such an impressive piece of footage. Let's see. So it's going to start back up here hopefully soon. So this glacier here is the fastest glacier in the world. It's called the Jakobshavn Glacier. It's in Greenland. It calves off on the west side of the ice sheet. And it's believed that it was an iceberg from this glacier that actually did sink the Titanic. So despite the humor before, it really likely did sink the Titanic. And we're just going to watch this thing break off again here. And so understanding the physics behind why these cracks form, how often they form, how quickly you can get the ice away from the front. And I'll watch it all rotate here because it's hydrostatically unstable and it flips over, and then this one behind it will go too. Now, there's so much energy released from that event that you could measure it on a seismograph in North Dakota. That single event was registered in North Dakota on a system used to detect earthquakes. So there's glacial quakes that just come from so much energy being released from these things. So these are the systems that we're dealing with. And you can see that going out and measuring one is nearly impossible. And so that's where we come from space observations. So the next part of the talk, I'm really going to talk about glacier health or mass budget. So that's what I spend a lot of my time doing. I try and figure out how much is going into the system, how much is going out of the system, and then if I know those two, I can figure out whether the ice sheet is either losing mass, so it's contributing to sea level rise, or if it's gaining mass, then it's taking away from sea level rise. So this is called, it's trying to achieve mass equilibrium, not much different than thermodynamic equilibrium. So NASA has a whole bunch of sensors. Some of them are future, the NISAR mission, and they all measure different aspects of glaciers. So one of my favorites is the ICESat laser. It died in 2009. It's a satellite that was orbiting Earth at about 300 kilometers above the atmosphere, 300 kilometers above the surface. And it would fire a laser pulse, and it had a very, very precise clock on it. So it would register when that pulse left. It would wait for it to bounce off the surface, and then it would retrieve it in its telescope. And by knowing the exact time it left and the exact time it arrived, and then you know how fast it was traveling, you can measure the elevation very, very precisely. And if you come back and do that again and again and again, you can actually see the surface change through time with very high precision. GRACE satellites, developed here in part, are the first satellites to measure outside of the electromagnetic spectrum. Right? So if you open up a remote sensing textbook or an Earth observing textbook or something like that, it will all start with, every sensor measures some part of the electromagnetic spectrum. Well, that's no longer true because we have a set of satellites that are able to measure changes in gravity, which is just phenomenal. So these two satellites chase each other continually around the globe, and the little changes in distance between those two satellites tells you what the gravitational pull is. And you can see the pull of gravity change over time. And the largest places it changes is where ice is leaving and entering into the ocean, or ice is leaving the ocean and going on to land. So you see these large changes in gravity, and I'll show you some of the figures later from that. NISAR is a mission that's also being done in part here. It is going to fire radars at the surface, and by looking at very slight changes in the position of the wave, you're able to map the surface velocities with incredible accuracy, and we'll be doing it very frequently once the satellite goes up. And then we also have more conventional satellites like the Landsat missions. The Landsat missions have been operating since the 1970s, and it's basically just like a very, very powerful camera pointed down at Earth, and has provided invaluable information of how the planet is changing. Now, the units I like to use are gigatons. I have no clue what it means. I plotted it up in Google Earth one day, and these are 3 gigatons with the Empire State Building for the standard reference in front. It's just a big cube of water, okay? So it's 1 billion tons of water. And so I'm going to be talking in hundreds of gigatons. So large units, that's what I deal in, large units. Okay, so I'm going to walk you through what's happening now. This would have been my whole talk before, but since about 2002, we've had launch of satellites that make this easier and easier and easier to the point where we can now start looking at other things. And so I can actually tell you pretty much what's happening today with the ice sheets. Okay, so the 2 major ice sheets are the Greenland and Antarctic ice sheets. So Greenland holds about a total of 6 meters of sea level rise, 6 or 7. Antarctic ice sheet holds about 60 meters of sea level rise if melted completely. They're not going to melt completely anytime in the next millennia. But we're looking at small changes in very big numbers which can have meaningful impacts. So let's start with the Greenland ice sheet. This is a picture of the flow of the ice on the Greenland ice sheet. This was measured with those radars that I was talking about before. So if you look at the purple colors, that's where the ice is flowing fast. And the glacier that you saw calve, that big calving event, is right here. This is the Jakobshavn Glacier. So that's what we were looking at there when we watched it calve off. So the ice is flowing down into the ocean, and there's all sorts of different things you can do to change whether it's gaining mass or losing mass, but you can just think of it as 3 ways. Either you change the amount of precipitation going in, you change the amount of melt going out, or you change how fast the ice is flowing. And when we look at the GRACE record, so this is changes in gravity over time, we can measure how much mass is being moved around on the ice sheet. And so this is for Greenland, and you see these little wiggles in the record here, starting in 2002, and we're going all the way down here to 2016. And these little wiggles here, that's winter, right? So the freezing stops, and you get the snow accumulating on there, and then the melt comes again the next year, and then in winter it starts to gain, and then a melt comes. And then underneath all of this, you'll also have changes in how fast the ice is flowing. And so that's exporting mass away. And so we can see that the average rate for Greenland, it has been losing 281 gigatons per year, right? So that is, in under 4 years, it will lose 1,000 cubic kilometers into the ocean. So it's definitely the biggest single source of sea level rise right now. That might not hold into the future, but we'll see. Okay. So here's the Antarctic ice sheet, much larger. This is larger than continental United States, so it's quite large. Now, in the Antarctic, there is very little surface melt. So we're not necessarily at this point worried about the atmosphere warming and then that causing a whole bunch of melt to go into the ocean in the Antarctic. That's really not the case. What's happening here is that the oceans have a lot of contact with the ice around the edge. And as the oceans change in circulation, that's causing some changes in flow. And so we're looking at all the big ice streams here again. And the place we're looking at most, and you may have heard it in the news, is this part right here. This is the West Antarctic ice sheet. And this is where everybody should be most interested. And that's where we have a lot of research going on, and it has the potential for rapid response. I'm going to show you an animation later that will illustrate that a little bit. Okay, so we can look at the GRACE record for the Antarctic. You can see that it's not as clear of seasonal cycle, right? Because it's kind of always winter a little bit. You don't have those big pulses of melt, so it does warm up in the summer, but you're not going to lose a whole bunch of mass from meltwater. So a lot of it's driven by dynamics. And then there is a little bit of seasonality just with storms, how they roll in and things like that. So over the GRACE record, it's lost about, on average, 118 gigatons per year. So it's also losing mass, but not nearly at the rate that Greenland is losing mass right now. And yet, the Antarctic causes us the most concern and is probably where most research is focused these days. Okay, so I've changed the timeline on you here. It's a little bit nuanced, so I'm not going to explain it. But a good way to think of it is that present-day sea level rise, the rise that we're measuring, the record I showed you, about 1/3 of that rise is being controlled by loss of ice from the Greenland and the Antarctic ice sheets. Now, what about all the other ice on Earth, right? So that's typically what people think of when they think of glaciers. They think of skiing in the Alps. They think of the beautiful glaciers in Alaska when you go on the cruises. But really, that ice is kind of pathetically small. If you took all of that ice and you put it into the ocean, it would only raise sea level by about 1/2 meter, right? So it's a fraction. It's about less than 1% of all of the ice contained in those two giant ice sheets. So my colleagues and I set out in 2013 to try and figure out, well, what is that contribution to sea level? And what we found is that because all of that ice is actually located in areas that are quite a bit warmer already, that if you change the temperature even a little bit in those areas, they have to melt, right? So in the Antarctic, if you raise the temperature by 2 degrees Fahrenheit and it was minus 40 degrees Fahrenheit to start with, you're not going to get any melt. But if you're if you're in the Himalayas and you increase the temperature by 2 degrees, well, it was already at 0 degrees, so all the extra energy has to go into melt. So you can walk around and do this for all the glacier regions on Earth, and you find out that the contribution from that other ice right now is actually significant. And over that same period, you can kind of break it down like the ice sheets were contributing about 1/3 of sea level rise, the glaciers were contributing 1/3 of sea level rise, and then the other third was coming from thermal expansion, so that's when the water warms, it gets a little bit less dense, it expands a bit, and then also some other processes that are a little bit nuanced. But the point of this is that if you're interested in sea level rise, you're really interested in ice. And that ice is going to dictate where sea level goes into the future. And so that's why a lot of focus is being paid attention to ice. And now the big question is, what happens next? Okay, so you're not concerned about the 3 millimeters that it's going to rise the next year, and you're not too concerned about the 3 millimeters that it's going to rise the year after that. But what we want to know is when you start going out 50 years, when you start going out 100 years, how much can we expect for sea level rise? And that's where we're putting most of the effort. So what does that require? Well, that requires modeling, numerical modeling, right? We're trying to anticipate what will happen in the future, and it's a future that we've never seen before. And so what we do is we try and take all of the information that we have from a relatively short observational record. We try and determine what all the physics are that govern ice and all of these other complex things, and we put them into these models to try and simulate what the future might hold for us. And that's where the state of the art is now, is now we know what the sea level is right now. We know where it's going in the future. It's going up. We know a bound of how much it's going to go up. It's going to go up somewhere between 0.5 and 1.5 meters in the next century. And now we're trying to narrow that envelope. And to narrow that envelope, we need a lot of information on very detailed things that we then put into these models to try and simulate. And I'm going to demonstrate why that is so important. So this is a paper that was published last year in Nature magazine, which is a very high-profile publication. It's received a lot of press. And on your left, you see a simulation in a high CO2 climate. So the one on the left is if we took no action. The one on the right is if it's overly optimistic at this point. I think the analysis shows that there's no possibility of hitting that scenario for emissions because we've already kind of overcommitted at this point. Now, the two simulations are running. They're being forced by two different climates. One is a climate that is much warmer. That's the one on the left. The other is a climate that is much more similar to modern day. That is the one, on your right, on the left. We're going to watch it go through once more, and now keep an eye on West Antarctic, right? So this ice here, it's all grounded below sea level, which means that the ice is currently sitting on a bedrock that is below sea level. And so once the water starts to eat away, you can have irreversible retreat to the point where it starts to continually dump water into the ocean. Now, this is driven by two different climate scenarios, but equally, I could take a different model of ice, and it would also produce a different result. And that's because the models are so sensitive to what happens right where the ocean comes in contact with the ice. We have all of these complicated things that we like to look at. We like to look at right here, it's a grounding line. We like to see if that's moving inland. We need to know what the bedrock looks like underneath. If this bedrock went up like that, we would have no concern at all. That means that as the water started to eat this ice away, there's not much it could do. But if we go and we measure the bed and it starts to get deeper behind the glacier, what we call a retrograde slope, then we start to get concerned because now that ice, if it melts a little bit, it can continue to pull back, because if it pulls back a little bit, well, now it has a bigger face and it can get rid of more ice. And then it pulls back a little bit more, and then it has a bigger face, and so it can continue to dump ice into the ocean. And so these are the parts that we focus on, and I'll show you some of the highlights of that. Okay, so we're analyzing the observational records. We're analyzing the in situ records. There are several airborne campaigns that have all sorts of different instruments on it, and they're measuring all different properties of the ice. But the problem is we only have a very, very short record. People only got interested in this type of question only within the last 10 to 20 years, that it's really become at the forefront. So we've been playing, within the discipline, we're playing a lot of catch-up. And one of the areas that's very interesting right now is looking at the ice that's actually floating. So the ice has come down from interior Antarctica, it flows out onto the ocean, and there's these massive pancakes of ice the size of continents, the size of states. And we look at how much the ocean is melting that ice underneath. If the ocean starts to melt it a little bit more, then that means that ice will be more weak. If that ice is more weak, then the ice behind it can start to flow faster into the ocean. And now I'm going to show you a simulation of the types of things that are being done here and elsewhere, where people are actually coupling these fantastic ocean models to the ice sheet processes now. So these models are able to communicate between the different disciplines of ice and ocean. And they're simulating how the water goes underneath the ice shelves, how that interacts, and so that we then try and anticipate what the future ocean will look like. If we know what the future ocean will look like, we can then try and understand how that's going to affect the ice shelves, and then possibly how they'll react into the future. Less understood at this point are things that can happen very rapidly. So this is the Larsen B ice shelf. Now, in 2002, it rapidly collapsed. The image for size, from top to bottom, it's probably about 100 miles, right? And this is one of the smaller ice shelves. And so you've probably heard in the news lately that there's Larsen C, which is his neighbor just a little bit further south, has a massive crack that's grown about 12 miles in the last 2 months. And there's a big tabular berg that's about to calve off. The implications for sea level rise aren't much. It's actually, it's not that significant. We don't expect much changes in the glacier. It's not really pushing back on anything, so that's fine. But in this case, this ice was actually pushing back on something. And so now watch over a matter of a couple days what happens to the ice shelf here. Right, so from February 23rd, March 7, and then the whole thing's gone. Right, and the whole thing just flushes out. It collapsed within a couple days. And so we're trying to understand these types of processes so that we can anticipate whether that's likely to happen to other ice shelves. If it happens to the larger ice shelves, well, then the ice could definitely contribute to sea level rise. In this case, all the ice behind it started flowing faster. So this happened in 2002, and so now we can go look at how fast they're flowing since these events. They've all sped up, but because in Antarctic terms this is relatively small, it doesn't have much meaning for sea level rise, but the implications of other ice shelves is what we're interested in. Okay, let's see what happens here. It might just be loading. Okay. This is a beautiful image if it would play. So I'm gonna talk through it. The graphic's beautiful, but you don't need it to understand the concept. And that is, remember when I was showing the water flowing over the ice sheet, and I said that it came down and it reached the bed? Well, the first hypothesis was that, okay, it flows across the ice sheet, and then it goes down, it reaches the bed, and everything speeds up. Well, things aren't quite as gloomy as that. What we found out is that the water finds its way across the ice, it goes down, and at first, in the first part of the season, everything speeds up. But then by midsummer, these huge channels form underneath the ice sheet. And that means that all of the water underneath the bed of these glaciers is all channelized. And so it's no longer letting the glacier slip. And so you actually see these massive seasonal swings in how fast everything flows in Greenland. And you see this all around Greenland. Almost all of the glaciers have some sort of seasonal pattern in how fast they flow. And we look at this information because here we have big changes in temperature happening over 12 months. And we can use some of that information to try and project what will happen into the future. Okay, so that's where we're at. That's what we're doing. So when I go and I sit at my desk and I try and come up with new results that will have meaning to sea level rise, we're trying to answer those questions. And those are the questions that we're focused on. And thankfully, we have a series of missions that's going to go up over the next few years that is going to radically improve our understanding of these processes. So one of the missions that we have, this is actually going to be mid-2018 now, is ICESat-2. Now, ICESat-2 is a sensor that is going to be orbiting Earth at about 300 kilometers, and it's going to fire a burst of photons down to the Earth. And those individual photons are going to bounce off the surface of the Earth and get caught in the telescope. And each individual photon is going to be measured, each individual time of travel for each of those photons. And so we're talking the smallest quanti of energy now that we can measure. I mean, I find it amazing. So if I set this instrument up in Boston and you were standing in New York and I pointed at you, I could tell you whether you were standing off the curb or not, right? I mean, the precision with which we can measure these things is incredible. And we need such fine measurements because when you have something the size of a continent and you want to know if it's contributing to sea level, it doesn't take a lot of change before it really starts to matter. And so you have to measure it with very high precision. The other mission that's being partly done out of JPL is the GRACE follow-on mission. So I talked about the ability to measure gravity from space. Well, now we're going to continue that because it's been such a valuable record. But we're going to have a new instrument on there that's going to be tested out, which is called a laser interferometer. All you need to know is that the current system, which has a microwave interferometer, can measure the distance between those two satellites. So one satellite is equivalent to down in San Diego, and the other one would be up in LA. So they're about 200 miles apart. And the distance between those can be measured to 1/10 of a human hair with the current system. The new system is going to be 10 times more precise than that. So 1/100th of a human hair, it can measure the distance between those. So just as an engineering feat, it's incredible. And because you can measure the distance between those satellites so precisely, that means that you'll be able to measure changes in gravity even better than the original mission. And then lastly, a little bit further off, is we have a collaboration with the Indians, and it's the NISAR mission, and we're going to be looking, this is going to be a radar interferometer. All it means is that we'll be able to see displacements in solid Earth. So if there's a volcanic event, we can actually see the bulge of the volcano starting to grow a bit. If there's an earthquake, we can actually see what side is slipping versus another and how much it moved. And for the stuff that I do, we can see how fast the ice is flowing into the ocean. But more importantly, we can see how the flow of the ice changes as there's changes in ocean, as there's change in atmosphere. That's going to give us a lot of information that we can then feed into models to try and provide better estimates of what happens in the future. Okay, so now I just want to pull back and kind of finish this off. So because of the efforts by NASA, by ESA, our European counterparts, by other countries, there's been a rapid evolution in our understanding of glacier and ice sheet processes. So remember, the impetus just wasn't there before. So compared to fields like biology or chemistry or physics, these fields have been at the forefront of science for a very long time, and we've only been on the map for the last 2 decades. So we're really rapidly improving our understanding of these systems and how they work. The reason we're doing this is because we want to know where we're going, where we're going to end up. So given a set of different options, which in this case are emission scenarios, we want to know what those different pathways look like. And so, as I like to say, if you're going to jump off a cliff, it's better to look at your landing than close your eyes. And so NASA's job is to keep their eyes open. And then lastly, the question that we're working on now is not if this is going to happen. That has already been determined. We know that sea level is going to rise. We know the atmosphere is going to warm. We're now working on the details of how much and how fast. So this is an incredible image captured by a NASA satellite of the Earth. And on this screen, it looks quite large, but we're just a tiny little speck on this map. But when you zoom out far enough, it's really hard to see our planet. So this is a beautiful image captured by the Cassini spacecraft of Saturn's rings. And I find this one of the most kind of bone-chilling and inspirational images, because what you can't see in this projection is that there's 4 little pixels in one of these rings. I'll kind of point out where it is here, but right along one of these rings, right in here, there's 4 little dots. Looks like a little speck of dust. And that's actually Earth was captured in the image when they made this image. So I'm going to blow that up for you here. Those little dots, there's Earth in those rings. And as of now, that is home to all known life, which is slightly intimidating. But what I like to say is that no matter what decision we make on what path we go, there will be no one to judge us. It's just up to us at this point.